So the second type of problem is called the common ion effect. So we know that if you put lead chloride in water, it is not soluble. Only a very small amount will dissolve. And we calculated that in the last problem. We found that this much and this much will dissolve. Okay? Now, what happens if I add, let's just make this problem simple. Let's say I've got 1 liter solution, okay? 1 liter total solution. Now what happens if I add sodium chloride? And let's just say we're going to add 15 grams, okay? So what does sodium chloride do? We know that sodium chloride breaks apart completely, okay? So 15 grams sodium chloride would be, so we're going to find the molarity. Sodium weighs 23 plus chlorine. And I'm in 1 liter of solution, so my molarity is 0.256 molar of the sodium and 0.256 molar of the chloride, okay? Well, what happens when you add a stress to a system? Le Chatelier's principle says the system will shift in order to adjust the stress. So I'm adding chloride. So if I'm adding chloride, which direction will the reaction shift? It'll shift to the left to compensate for the stress. In this case, the stress was adding chloride, so then the reaction is going to shift left, okay? Now the question is, how much will it shift left, okay? So now we have to do a little bit of different type of calculation. All right, so this is a solid, so we don't care how much we have initially because it's not included in the equation. Now, my chlorine is going to be the molarity. Because I'm dealing with 1 liter, I can just add these molarities together, okay? So my molarity is going to be 0.02 0.2890. And all I did again was I just added these two together. Added this number to this number. And I can do that because they're in the same solution and the volume did not change. Okay? If the volume changed, I'd have to recalculate the molarities. So we already said we are going to shift left. So I'm going to lose this, gain this. Now, how you define x is up to you. But if I'm losing x of this, I would lose half as much as this, because the ratio is 1 to 2, okay? Now, if you don't like to have fractions, then you would define your x differently, and you'd say, okay, well, I'm going to be shifting left, and I'm going to lose x of this, and therefore I'm going to have to lose twice as much as that. Okay, so if you don't want to deal with fractions, you can define it that way. So at equilibrium, doesn't matter because solids aren't included. 0.0165 minus x, 0.289 minus 2x. My expression is, don't forget that the chlorine is going to be raised to the second power. So then I really should put AQ and AQ. So now we can plug in our numbers. The KSP is still the same. We look it up on the table. KSP for lead chloride is 1.6 times 10 to the negative fifth. I've got 0.0165 minus x, 0.289 minus 2x, and x is not going to be a small number, so we can't throw it out in these problems. We're going to have to work out quadratic equation. So going to have to distribute. All right, hopefully I did that right. Okay, so now I'm going to set this equal to 0. And now let's do the quadratic equation. So I'm going to have negative 0.322 plus or minus the square root of negative 0.322 squared minus 4 times 2 times 0.00475 all over 2a. If you end up with a negative molarity, you just disregard that one, okay? Oh, guess what I forgot to do, guys? I forgot to square. So, way to go, Mr. Strauss. Here I told you guys to forget to square, and I forgot to square. So 1.6 times 10 to the negative fifth. In this case, this x should be too small because of the square. And if it's not, well, then we can always go back and solve a trinomial. All right, so now, hopefully this is a little bit easier. Okay, I'm going to bring this over to the other side. All right, much better answer. Okay, so that's x. So what does that mean at equilibrium? So if that's x at equilibrium, my lead ion is going to be 0.002 molar, and my chloride ion is going to be 0.256 molar. Okay. All right. And so that's how you solve a common ion effect problem. All right.